So hello nerds, this is Suman and in this video we're gonna discuss about a beautiful differential problem of smoking cigarette. So basically when I was in first year I had heard about the differential equation and the decaying equation. So an equation that decays exponentially with respect to time. So and I got yesterday a thought experiment. A cigarette can be an example of that decaying thing. So I put n and I made my own differential equation type version in order to check whether the math is consistent with it or not. So for that purpose, I had actually bought uh, five same brand cigarettes, right? So for the sake of science and for the sake of maths, I'm doing this. So don't judge me by its cover, right? So basically, I have four cigarette of same brand. It is actually Kukuri brand. So basically, I had made an differential equation that I would like to firstly show you, and whether it works or not, we will check in the last video where I will be trying to do for the sake of math, right? So let us go and let's see what a differential equation of the smoking cigarette will be, or how the length of cigarette changes with change in when you inhale or exhale that smoke, right? So let us go and do a simple mathematics how it really works, and let's do an experiment also. So I had collected data from my friends, so I would like to show you the data I had collected from my friends. So I will be showing you this within a time, and let's go to the whiteboard and let's see what it could be the differential equation that governs this. So first I would like to say, don't judge me, or whether you judge me or not, it doesn't matter. I had just done this experiment for the purpose whether the math really works or not, and if this math really works, you can do the experiment with your friends using the same relation depending on the length of your cigarette. So basically this is very small cigarette, and this is Kukuri brand. This is the brand of our country, and it has average of length 6.7 centimeter, right? So it's whole length. And the when the people actually take this, right, so they do not smoke all this part, they only smoke up to here. So up to here, because they do not test the filter, right? So let's go to the whiteboard and do a simple differential equation, made a simple differential equation that is governing all this phenomena. So nerds, let's make a simple mathematical model describing this phenomena. So firstly, I would like to make a cigarette so that it might looks familiar to us. So this would be my cigarette, right? And let us assume initial length of the cigarette is L naught. So L naught be our initial length, and we do not actually smoke the whole cigarette. We take this out, we throw it, right? So this is the filter part, and that we use to throw it. And let assume this be our length small l, because we are interested in this phenomena, not in this. So this is not the case, this is not the thing of our choice, because but this is the thing that we want to measure. So this much length is going to be l minus l naught. Okay, sorry, l naught minus l. Okay, so I am going to make an equation that might describe this phenomena. So basically we are interested in the rate of change of this cigarette. So how the length of this portion changes when we ignite it with a lighter, and it goes on changing. So the length of this cigarette goes on changing when we ignite it with respect to time, right? So the rate of change of length of cigarette is directly proportional to the initial length L. So L be the length. So the more you have length, the more length will going to change with respect to time, right? So this could be negative sign, because the length of cigarette is going to decrease with respect to time, because after some time it would be this much, after some time this would be this much, and sometime this would be this much, and it goes on decreasing. So the rate of change of length of this portion is directly proportional to the length, right? So, and second thing, the cigarette that we are taking we have to inhale and exhale out. So the faster you inhale or exhale, the faster the fire will catch up the different portion and it will change the length of cigarette. So I am saying our rate of change of length also depends on the number of puffs taken per unit time. So the faster you take puffs, the faster the length is going to change. I think you might have known. If you did not smoke, also I don't. So if you didn't smoke, but let us we say that is a puff. So the faster you do inhale and exhale, the faster the length is going to change with respect to time. So let us assume this the R be our the number of puffs per unit time. So it is going to be our number of puffs per unit time. Okay, okay, it works. So we can write it like small r. Okay. So now combining these two equations, we get dl upon dt is directly proportional to rl. Okay. So for our whole experimental phenomena, we take the average of this thing, and for that context, our r is going to be constant. That is going to be independent of time because we had already taken per unit time. So it might not blur our result or might not destroy our result. So negative dl upon dt, when you remove the proportionality sign, you have to add some constant. That would be our lambda, gamma, L. Okay. So now take this negative sign over there and you will end up getting negative lambda R L. And this is the differential equation that governs the following phenomena. Right. So now we have to make an in terms of length. So if you take this L over here and take dt over there, it is going to be dl over dl over L is minus lambda R dt. Okay. So for the whole phenomena, we have to integrate dl over L and minus lambda R integration of dt, and you have to take limit. So when our t is 0, right? When our t is 0, when our time is 0, before igniting, that would be our time 0. The time is 0, and the time 0 corresponding length is actually L naught. Okay. So when we ignite this with lighter and we started inhaling and exhaling the smoke, the time will be our certain time t when we reach up to here. So this would be our t. And when you reach up to this portion, your corresponding length is going to be L naught minus L. Right? So if you know the derivative integration of dx over x, it is actually ln x. So it would be our ln L naught to L naught minus L, and that is minus lambda RT. Okay, this looks quite familiar. Okay, this looks quite familiar. And when you take, okay, let me do this. L naught minus L minus ln L naught is equal to minus lambda RT, and it is in the form of log A minus log B, and it is going to be L naught minus L over L naught. It is minus lambda RT. So it would be our L naught minus L over L naught is equal to exponential negative lambda RT. So this would be our another form of the same equation. And let me just write in terms of our small l how our l is going to change with respect to time. So I am taking this L naught over here, and I got L naught minus L is equal to L naught exponential negative lambda t. Right? Exponential negative lambda t. So when you take your L naught here, it would be positive, and if you take this here, it would be, before explaining I had to show you this. You might immediately understand this. Yes. So L is function of our time because the L depends on time. The more it depends on time, because when we start inhaling and exhaling with respect to time, the length is going to change. So L is function of time then, and that is going to be L naught 1 minus exponential negative lambda RT. So this would be the differential equation. This would be the solution of our given equation for this differential equation. So this would be our solution. So you can actually see the length actually change exponentially. It decays exponentially. The length actually decays exponentially. So if we plot the graph, So actually if you plot a graph of L and time, you will end up getting a curve like this. You will not get a straight line. So this would be my differential equation, and for this experiment to be done, I had calculated various data that I would like to show you in the next session. So up to here, this would be my differential equation governing all these phenomena. So nerds, I'm back with real data that I had gathered from my friends. Or you can simply say that I had smoked. You can say whatever you want. But I had collected the various data. So let's go and see what the data actually represents, and let us assume for any number of puffs, the what will be the corresponding hour length. So basically you can see from here, let me just put it here. So the first person I had cancelled because there is less number of puff and it does not gives the accurate reading. But let's do for our second person, the length is this much for that cigarette, right? And L naught is the total length, and L is the portion that we are inhaling and exhaling during the whole time. So there are no total number of puffs 60, and the time taken for that 60 puff is 60 seconds. So the total number of puffs per unit time is generally 1 second. And if you had noticed, the number of puffs per unit time is our R. So in terms of R2, I had written for second person it is R2, and it is number of puffs is 1 puff per second. So basically my friend is taking 1 puff within a second. So you can actually think of it as how fast he is actually doing all these things. So and for third person, you can see the length is corresponding length is this much and this much, and the corresponding number of puffs per unit time is 0.91 puffs per second. So up to here the data is, I think the data I had taken is quite good. And for the fourth person, the number of puffs is actually, sorry, this is the number of puffs, 62 is the number of puffs, and the corresponding time is 55 seconds. I have just mentioned it here in the wrong way. And the number of puffs per unit time is 62 puffs upon 55 seconds is gives you 1.12 puffs per second. So for fifth person, I had calculated right this, there are 70 puffs within a 68 second, approximately 1.02 puffs per second. So the average puffs per second. So basically in first we had calculated R1, R2, and here R3, R4 and R5. I'm taking the average of all these and I get R is 1.0125 puffs per second. So there might not be fraction of puffs per second, there might be one. So we can arbitrarily say that this is 1 puff per second. So the average length of whole cigarette that I had taken during the experiment is 6.8, 6.9, 6.9, 6.8 divided by 4, and it is came out to be 6.885 centimeter. So average length of L is nothing but just the portion that we going to inhale and exhale during the whole process, and it comes out to be 0.51 centimeters. Okay, so and for the whole scenario, I had calculated the lambda, which is our rate constant during this experiment. So I had got various lambda value. You can actually see from here using this formula. I had calculated for the second person that is 0.022 per second, and for third person I had made a general formula, look this, and I had substituted value and I got lambda 3, lambda 4 and lambda 5, and average of all these is going to be 0.02225 per second. Okay, so from our calculation, L naught average we got is 6.85. The rate number of pops per second is 1.0125 per second. Lambda average is 0.0225 per second. The L average is 5.1 centimeter. From our formula we can substitute, and we are going to do the experiment for the expected value of L for 40 pops. Now I am going to blow the cigarette, ignite the cigarette in the video, and I am going to take the 40 puffs, and I'm going to calculate the corresponding length that our math predicts, and also going to check the remaining portion of cigarette that we had used. So I think the 40 puffs is actually going to be very much high. Let us go for only, what would you say, 30. Okay, let's go for 30 puffs. So I had extracted various data from the different person. No, it is not actually from different. I would like to mention you that I had done this experiment and I actually take the puffs. So these are my data, and I had taken permission from my mom, not from my dad. If my dad says this, he's going to. No, I don't record the smoking that I has done in this video. But in the later on, I have to do that also because I have to show that. So these are the data that I had collected during the whole scenario, and now I'm going to use this data. Sorry, I had used this data and make an differential equation, and I would like to take 30 puffs, and I would like to calculate the length that we are getting from our formula, and going to measure the length using the ruler, and whether this value match is going to accurately match the result or not. So let us see. So nerds, up to there, we found a mathematical relation that actually describes our smoking cigarette behavior. When someone inhale or exhale that, this mathematical equation automatically came into play. So uh, this is a mathematical expression I'm giving you. And if you had courage, if you can take that bold decision, you can actually experiment by yourself and and you can calculate the amount of length change for a particular instant of time within a certain range of puff, meaning how many times you are inhaling that thing. So if someone is not doing your experiment and you have to take that bold decision in order to check or verify the math, so I am doing this. So I am going to calculate the length for the cigarette uh, that I had taken for reference for 25 puffs, and for the let's say 35 puffs or 30 puffs, whatever we say. So I want to set a timer for that purpose, and I would like to do the experiment now. First we are going to do for 25 puffs, and it is going to be fast and furious, as fast as possible. So let's do that. So okay, for 25 puffs, bitter. So actually for 25 puffs, I got a time of this much. Whether you see it or not, it is 24 second, and I would like to show you in my ruler that the expected value of this experiment. So I would like, and now I am placing my cigarette here for the length calculation, and from here you can see, so actually the length is measured from 2 dot, so you can see from there. Let me do that. So from here our length is approximately, we have to say 2 centimeter, right? So for 25 pops, so basically for 25 pops we got length, our approximation of length is 2 centimeters, right? So I am taking this data for 25 pops. For 25 pops, the time we got is 24.22 second, and the corresponding length measured by ruler, because we have to verify with our mathematics, so corresponding length due to ruler is actually 2 centimeters. So approximately it is not actually 2, because some of the little teeny weeny parts are away and behind the ruler. So I am just saying it's a 2 centimeter. So if our result approximate up to 2 and 2.1, 2.3, we verify that it actually works. So now I'm again doing the same bold decision and going to calculate for 30 puffs. So let's do this another time, and I have set up in my same thing. So let's do for 30 puffs. Okay, I had done it for 30 pops also, and the corresponding time I get is for 30 pops. For 30 pops, the corresponding time is 24.80 second, and the length I have to measure from ruler. So I would like to first balance it in our position. Okay, so I'm going to show you from, so from ruler you can see from here the length is about approximately uh, whatever we have to call that length. So the length is actually up to 2.5, nearly 2.5. Let's approximate this length. So it actually nearly up to 2.5. So length measured by ruler is up to 2.5 centimeter. It is actually 2.5 centimeter. So now I have to do the calculation in my board in order to show you whether this formula actually works or not, and we have to calculate the error. So if you had heard about this thing, it is said by one of the famous professor and one of my favorite professor, Walter Lewin: an experiment without error is not an experiment. So we will be going to find the error of this result also. So I would like to set up my equation in my board, and I would like to show you with the mathematics, and using the calculator we will find the expected length. So let's do that. So nerds, up to here I had calculated my two major experiment results for 25 puffs and for 30 puffs. So for 25 puffs the corresponding time is this much, and the length measured by using ruler is approximately 2 centimeter. And for 30 puffs the time taken is 24.80. Yes, it obviously takes more time than this. Okay, and the corresponding length measured due to ruler is 2.5 centimeter, right? And the lambda, the decay constant for the cigarette, and the R is the number of puffs per time, we had already calculated. We are using the same value for both cases. Only the change in value is going to be the time. So the time for 30 puffs could be different. Here is it's different, and the time could for 25 puffs is different. So only thing we have to vary here is time. So I had done for L25 is equal to 6.8 into 1 minus exponential. This is our R. Sorry, this is my lambda. This is my R into time. So for here also I have done the same thing, and I'm going to calculate whether it works or not. So let's do. So I had 6.85 into 1 minus shift ln negative 0.0225 into 1.0125 into 24.22. So you can actually see from here. This is my result, that is 6.85 into 1 minus exponential negative 0.0225 into 1.0125 into 24.22 second. And the length we had predicted, from the ruler is 2 centimeter. So it could be a deciding moment for us whether our formula actually matches our result or not. So I'm going to, and this is approximately 2.90. So it actually measures something very much strange thing, that is 2.90. So L25 is approximately 3. So I had already told you during our calculation we had left and teeny weeny part of that cigarette portion that we haven't included. That's why it's come out to be this much centimeter. So again I'm going to do the same experiment for our L30 puffs. So it is going to be 6.85 into 1 minus exponential negative 0.0225 into 1.0125 into 24.80, and this much. So you can actually see from here. So all the data I had taken is true, and I'm going to use equals, and it gives us 2.84. So L30 is approximately equal to 2.84 centimeter. So during this calculation we have approximated this value, and during this we hadn't just approximated. So that's why our result comes very much near or closer to this. And during this we got 3 centimeter. So we are going to calculate the error. So error can be 3 minus 2 by 3 into 100%. So it is going to be 3 minus 2 divided by 3 into 100. So it is going to be 33.33% error. So I forgot the actual formula for error. So I am doing another calculation. So you can actually say that which one is true. So I am using 2 out from here and taking 2 in divide. So 2 minus 3 divided by 2 into 100. And it is going to be 50% error. Okay, so one of these might be true. And for here we can calculate our error. That is going to be 2.84 minus 2.5 divided by 2.84 into 100 percentage. And this is going to 2.84 minus 2.5 divided by 2.84 into 100. Into 100 we got 11.05% of uncertainty, whether it is true formula or not. So I am doing another for error. The one might be true for, so it is 2.5 minus 2.84 divided by 2.5 into 100%. So it is 2.5 minus 2.84 divided by 2.5 into 100%. It approximately gives 13.6% is our error. So this is our error during the experiment. So nerds, up to here our result actually, one of the result actually matches our assumptions, because it approximation, under the approximation it matches, right? So and one result actually deviates more. So it occurs uh, due to that the fact that we didn't use the teeny weeny small portion of that cigarette, if you had noticed, because already I had told you I'm approximating it up to the length of 2 centimeters. So there might be some points, some extra factors that is going to be in that term, so it doesn't allow, we didn't take that under consideration. So that's why our data actually deviates from that. But for second example our data actually nearly matches. So it nearly matches to its result with 0.34% of uncertainty. So actually this might be a true relation, that a cigarette actually decays exponentially with respect to time if someone is inhaling and exhaling it. So whenever, and I guess so, whenever you might see someone actually smoking in public, or whenever you might get think about this video every time. So there was an idiot who has done this experiment and actually calculated how the length actually varies. So depending on my choice, I had done this experiment. So one can has a different rate of spreading, rate of puff per unit time, so it may deviates for other people, but the formula that I had derived actually works for all the three cases, every cases. So you have to put your the number of puffs per unit time and the time taken you have doing that amount of puffs and whatever you are doing. So in that case the formula actually holds, and the relation is L is equal to L naught 1 minus exponential negative lambda RT. So it actually holds true. So for this, bye bye.